Hi everyone. Today we will discuss about the last part of the CO3 about chemical bonding and molecular geometry. As we already discussed in last session about the chemical bonding, we make an approach how to draw the Lewis structure in every substances and every compounds. Then the next topic is you were allowed to make some approach in forecasting the kind of molecular geometry of any substances. Let's see, what is the molecular geometry? Well, we have the three-dimensional arrangement of atoms in a molecule, such as we have here. I give you some example of the shape of molecules, such as protein and DNA molecules. You can see that there's a very complex of geometric molecule, but the important thing that why we should make some forecasting about the molecular geometry is to understand about their chemical properties, such as the melting point, boiling point, density, or any other reaction that may goes with these substances. Okay, let's go to the general approach that we may use in the determine molecular geometric molecule. How we can make some experimental, or we can also determine the bond length and their bond angle. But in this session, we can make some simple approach, which is we use the valence shell electron pair repulsion, or we can short it as VSEPR models, which is we consider the appearing of electron pair, which is there are two kind of electron pair in the central atom, which is as lone pair electron or bond pair electron. So let's see how we can make a determination in the geometric molecule of any substances. First, I have a molecule in which we can separate it into two types. As I mentioned before, that the central atom, we have already learned about the central atom when you ask to learning about the Lewis structure. You have to first central atom and then which is the atom that take an action as the terminal. You know which is the central atom. Next, you can make two categories, which is the central atom with lone pair and with no lone pair. In the first, we have to make an understanding which central atom with no lone pair. In addition, you can make some visualization or imagination how if the lone pair exists. Okay, so basically, you have to understand about how the geometric molecule of any central atom that doesn't have lone pair in it. Okay, we can make some expression in order to make the simple formula, for example, as EBX or A as the central atom, and B is the bond atom to the central atom, which is X is the integer that may result in the number 2 to 6. Okay, what if the A, B, X with the X is 2, it will express as AB2. The simple compounds that could be follow this configuration is such as beryllium chloride, BeCl2. As you can see in the draw picture, this beryllium doesn't have any lone pairs. Because it doesn't have lone pairs, but it attached or bound to the two chloride, it makes the central atom space divided into two divided by two atom, which is bound to it as we see is chloride, but it make the same space, make the geometric molecule to these substances as linear. Okay, that is makes sense because there's no differentiation between the both of the atom that bond to the beryllium. The next, when I change the integer, which is x at 3, our configuration will be AB3, a central atom which bond 3 atom. For example, is BF3 boron 3 fluoride. We can see here boron, it doesn't have any lone pair, makes the space this dimensional space of the boron divided by 3 atom the same way, so make this geometric molecule of the BF3 as trigonal planar. Let's make this more simple way. Let's see if I have one central atom which is bond two atom and two of them is the bond pair, but there's no lone pair, so the arrangement of electron pair will be linear. Also, we can make sure that the molecular geometry will be also linear. For beryllium chloride, we have already discussed it. Yeah, let's see how if I have one central atom with three bond atoms, then there's no lone pairs on central atom. As we mentioned before, the dimensional of the central atom will be divided into three atom bond, so make them as trigonal planar in geometric molecule. Now let's see what if the AB4, which is the central atom, bond to four bodied atom, which no lone pairs, it will make the space of the central atom separate or divided by four atoms as the same way, make them in the geometric molecule also tetrahedral. Such as methane is one of the compounds that may express the simple example. Okay, let's see the next one. You can see here that in the exception of the chemical bonding, there are such of elements that not fulfill the octet rule. So as we can see here that the octet rule only follow by this. While AB2, AB3, this is less than octet rule, while for AB5, it means that the central atom could bond or could attach 10 electron or 5 pair of electron. How if the 5 pair of electron, all of them is bonded without any lone pair electron? You can imagine in the dimension, which is the arrangement should be like this. You can imagine that in the three dimension, the space of central atom divided by 5 atom with the same way, it will make them as trigonal bipyramidal. Let's see. This is the such as of example phosphorus pentachloride. The last one is AB6, in which this central atom could attach 6 pair of electron or 12 electron valence, which all of them as the bonded atom and none of them lone pair, it will result the geometric molecule in octahedral. Okay, that is the basic principle in order to understand the VSEPR model in the central atom without lone pair. Next, we continue how we can predict the geometric molecule from the central atom with the lone pair in its substances. Okay, see you.